So a set is simply a collection of items or elements. And typically, when we write a set, we use curly braces. We also call them as set brackets. So sometimes people might use parentheses, but the most commonly used notation is to use curly braces or set brackets. So how do we define a set? Well, one way to do it is to give a description. For example, days of the week. Let's say, let's take as an example, I'll call this set as C. Now, our class meets only on one day, and that day is Wednesday. So we have a word description. So the one day would be Wednesday. So the set C has one element, and that one element is simply Wednesday. If you take another class that meets on Mondays, Wednesdays, and Fridays, then we'll call this another class, say B. I would write it as Monday, Wednesday, and Friday, and it has 3 elements. So we can come up with as many sets as we want. So representing a set can be done either in words. So here I'm using days when a class meets. So that would be the, oops, it's not the right color. The word description for sets C and B. And what we did here, or what I did in writing C and B within curly braces is what we call the roster method. So a word description simply means that we're going to write out the meaning of the set. In this particular example, days when a class meets is the set. I have 2 different classes. One class is C, another class is B. What is the description of the set? The days when the class meets. The roster method simply lists out the elements that belong to the class. So class C meets on Monday, which is Wednesday. class B meets on 3 days, Monday, Wednesday, and Friday. So there is another method, which is the set builder method. And I can write a set builder method in a generic way as some element X. And that element X will satisfy some condition. So element followed by a condition. And that could be any condition, but it is the condition that is going to help us build the set. That is the reason why we call it the set builder method. So, for instance, as an example, if I define A equals X, and I specify a condition, X is an even number. Then that would simply mean the set A has a lot of possibilities. There are lots of even numbers, starting all the way from negative infinity all the way up to positive infinity. I don't have space to write them all, so I simply write it as element X satisfying the condition that X is an even number. That is the reason why we call this a set builder notation. So I can build a set mentally or physically, if possible, by looking at the definition. Here is another example. So the set B is any element Y, and this is the condition. Y is greater than 0, and less than 10, and Y is even. So the second case, the set B, has very few elements. In this case, writing it in this lengthy notation may not be a great choice. With set A, it is an amazing choice because I have infinitely many possibilities. Set B, on the other hand, it is easier to build the set and write it up. I want the element Y to be greater than 0, and it has to be less than 10, and Y has to be an even number. So that leaves us with only 4 elements, 2, 4, 6, and 8. Every single element in the set is greater than 0 and less than 10, and every single element is even. So what I pretty much did is I started with the set builder notation part here, and I explicitly wrote them out. I ended up getting the roster method. So roster method is where you are able to write out all the elements explicitly. It is possible with the set B. It is not possible with the set A, because set A has a lot of elements. Another set, a very important set that we use is an empty set. So an empty set or a null set is a set that will have no elements. It is denoted as open curly brace, close curly brace, or more conventionally, we just put, a 0 and a dash through it. It's called phi. It's for a null set. They are both one and the same. You can either write it the first way or the second way. And this is more, conventional. What's happening? Suppose I define a set. A set A is defined to be the set of purple avocado species. There is no such avocado as far as we know. So what I wrote here is a word description of the set A. If I write it out using the roster method, I know for a fact, as of today, there is no species of avocado that is purple. So that would be an empty set. You can either write it that way, or you could do that. Both are correct. Another example. So set of buses that fly. Now, this is kind of, weird example. By bus, I mean a four-wheel bus, a bus that goes on land, a bus that's driving on a road is not going to fly. If I said an Airbus, be an aeroplane, and it flies. So in this case, I'm referring to a regular bus that you drive on the road. So will it fly? No, that would be a null set. Let me give you another one, which would be in terms of numbers. Set of negative numbers greater than 48. Can you think of a negative number that is greater than 48? Well, I certainly cannot, because there isn't one. So C is an empty set. Again, in each of these cases, I went from a word description to the roster method. Rorschach method is where you explicitly write out the elements, but since this is an empty set, there is nothing to write. There are no elements inside the set. So now that we know how we define sets, and we know one of the types of sets, the empty set, the next thing is set membership. How do we denote the membership of a set? If element X belongs to or an element of the set, let's call it S, then we denote membership as X in S. That euro sign is what we call as in. So if I want to demonstrate that X belongs in S, then I would write it as X funky euro sign and followed by the set S. Going along the same approach, if element X does not belong to or not an element of the set S, then we denote the membership as same X, but it's not a member of S. So we put the euro sign followed by a cross. So we simply say X does not belong in the set S. So oftentimes the notation is used to determine if a statement is true or false by testing whether an element belongs in S or otherwise. As an example, is 7 in the set 0, 1, 2, 3 true? No, 7 does not belong in that set because that set has only 4 numbers. The 4 numbers are 0, 1, 2, and 3. 7 is not part of it, so not true. So if I want to write the truth, I can write it as 7 does not belong in the set 0, 1, 2, and 3. Is cat, as in animal cat, a member of, let's say, set of mammals? Is it true? Can I say that cat is a an element in the set of mammals? Absolutely. Cat is a mammal. So this is true. So the purpose of the notation is to write things in a easier way so that we can say, okay, this particular element belongs in this set. This set of elements do not belong to a set, and so forth. Oh, you may say, well, why should we bother about sets? Well, I can't talk about numbers or, all real numbers by explicitly writing them out. It's just not possible for me to write out every single number on the real number line. In a similar manner, I cannot write out different types of numbers. So the first one, a common set, is the set of natural numbers. If someone came up to me and said, I'm using a set of natural numbers, I would immediately know that the set n is 1, 2, 3, 4, 5, ... keeps on going all the way up to infinity. It'll keep on going. It's a set of natural numbers. Is -6 in n. So -6 is not a natural number. So no, -6 does not belong in n. Now I could take a natural number and I can write it in different ways. But again, it is going to depend on the length of the set that I'm about to write. For instance, if I define, as an example, G is the set of natural numbers between 2 and 6. When I say between, I'm not including 2, I'm not including 6. So I would write it as G to be 3, 4, and 5. So we started with the word description. And in this case, I'm able to explicitly write the elements out. So I moved on to the roster method. Sometimes we may not be able to use the roster method. Either you can do it as a word description or use the set builder notation. One such example, let's start with the word description first. E is the set of odd natural numbers. Now I want to write it as a set builder notation. So would it be possible to use the roster method? No, because I cannot explicitly write every single odd natural number in the set E. So I can use the set builder notation and say E, the set X, followed by the condition. So I put the elements, put that vertical dash, and then condition. So X is in n, the set of natural numbers, and x is odd. So I'm saying that x must be a natural number to begin with, and it has to be odd. So I simply use the set builder notation to express the set of odd natural numbers. Earlier I mentioned, well, the purpose of sets is to write numbers, especially when we're dealing with the real number line, and even natural numbers. You might have seen the interval notation. Interval notation would simply mean you start with a number and you end with a number, so from something to something. So interval notations and sets. By all means, when we write an interval, we are actually specifying a set. So an interval notation is nothing but an inequality. When I say x is greater than 5, then that is an inequality. If I said x is less than or equal to 9, that is an inequality, and it is also an interval. If I said x is 2 less than x less than 16, I'm saying that x is between 2 and 16. I'm not including 2, I'm not including 16, I'm simply looking at numbers between 2 and 16. Now keep in mind, x could be any number. It could be 3.1, it could be 4, it could be 7, it could be anything. So anytime you have an inequality, then we can write it either in set builder notation, or I can write it using the roster method. Either would work. Let's just consider the set of natural numbers to keep things simple. X is greater than or equal to 7. If I want to write it in terms of the set builder notation, I can take this inequality. I can write it as the set contains element x satisfying the condition x is in the set of natural numbers and x is greater than or equal to 7. Mind you, I'm doing this to show the connection between intervals or inequalities and a set builder notation. In this particular example, it is silly for me to go for the set builder notation because it's lengthy. I have to write it out. I could have simply said x is greater than or equal to 7. That's easy. And I made it clear that I'm only looking at natural numbers. So in a case like this, if I'm asked whether you should go with an inequality or a set builder notation, I'm going to say inequality. Well, is it possible to write a roster method? Yes. But I can't write every single one of them out. But I'll use the same trick that I did previously over here, using the 3 dots. In mathematics, when we put 3 dots, we refer to it as the ellipsis. And it means and so on. It keeps on going. So 1, 2, 3, 4, 5, and it keeps on going in that manner. So here, if I want to write x greater than or equal to 7, I would write it as seven, because I'm including 7, 8, 9, 10, ... That simply would mean 7, 8, 9, 10, and all other natural numbers that are greater than or equal to 7. Even with the ellipses, I will not go for the roster method, because the inequality is much more compact compared to the set builder or the roster method. So the first problem means x is greater than 5. In other words, 5 is less than whatever x is. So since we are looking at natural numbers, this would be 6, 7, 8, and 9. Because I'm including 9. So that would be the roster notation for that inequality. 6, 7, 8, 9. So part B, the answer is an empty set. Reason being, I want the number to be bigger than 11, less than 14. That would mean the set has only 2 elements, 12 and 13. And I want it to be a multiple of 5. Well, neither 12 nor 13 is a multiple of 5. So we have a null set. So we know that we are dealing with a set of natural numbers. So by definition, natural numbers start with 1, or start at 1. So 1, 2, 3, 4, 5, 6, because I'm including 6. So the takeaway here is when we have an inequality or an interval, it is actually a set. They are related. We just pick one way over the other in terms of representation so that we don't have to write things up explicitly.